Hi, welcome back to my session. This is E. Manjula, lecturer in electrical, GIOE, Secunderabad. So today's our session is about the maximum power transfer theorem. In the previous session, we have discussed about the statement of Norton's theorem, explanation on it, and the application of the Norton's theorem for a given circuit. The objectives of today's session are statement of maximum power transfer theorem and the derivation, the expression for maximum power transfer theorem to load terminals. Okay, and application of the maximum power transfer theorem to a given circuit. So known to unknowns, the expression for power is P is equals to V into I or I square R. Okay, so the expression for power is P is equals to V into I or I square R or V square by R. In a resistance, power will be consumed in the form of heat. Okay, always we have to remember the resistance will consume the power in the form of heat. Okay, as applied to DC networks, it may stated as, so the statement of the power maximum transfer theorem is that, or else the maximum power transfer theorem is, a resistive load will abstract maximum power from a network when load resistance is equal to the resistance of the network as viewed from the output terminals with all sources of EMF removed, leaving behind with their internal resistance. So here what this statement is saying that the the load resistance, it will absorb the maximum power, but when means it will absorb the maximum power when the network resistance, the total resistance in a network, when you when you observe from output terminals, then this network resistance should be equal to the load resistance, provided in the network all the sources of EMF are replaced with their internal resistance. Okay, at that time the total network resistance, when this network resistance is equal to the load resistance, then the maximum power will be absorbed by the load resistance. This is a statement. So that is what maximum power transfer theorem. Okay, so here let me see once. So let RL is a load resistance, small r here it is a internal resistance of a battery, and Ra is a total resistance of the circuit as seen from the load terminals, okay, from A and B. And Ri is equals to R2 parallel with R1 R. Okay, so we know that this should be replaced with an internal resistance. When we are finding out the total resistance, then R1 and R will be in series and R2 will be in parallel with these two series components. So that is why R2 is in parallel with R plus R1, that is the total resistance. Okay, So RL will abstract maximum power from the network when RL is equals to RA. Okay. So when this is equals to this proof. So we have to prove it. Okay. So here the circuit current I is equals to E divided by RL plus RA, and the power consumed by the load is PL. That PL is equals to I square into RL. Okay, but we know I is equals to E divided by RL plus RA. Okay, so I square, so E square into RL into RL plus RA whole square. For PL to be maximum, so for PL to be maximum, what we will do? We will derivate it and equate it to 0. So dPL divided by dRL is equals to 0. Differentiating equation 1 and simplifying, we will get 2 into RL is equals to RL plus RA, or RL is equals to RA. Okay. So you have to simplify this equation. So what is PL? PL is equals to E square RL divided by RL plus RI whole square. Okay. When you derivate it, when you differentiate this with with respective of RL, then you are getting 2 into RL, which is equals to RL plus RI. Okay. So this RL will come here and you will get only RL. So RL is equals to RI. So hence proved. So always remember that the total network resistance, when it is equal to RL, then the maximum power will be transferred to the load. So hence maximum power is E square divided by RL. Okay. So the maximum power is E square divided by RL. How it has been calculated? So we know that the power is equals to E square RL divided by RL plus RI whole square. So now we came to know that RL is equals to RI. Okay, substitute here in place of RI, RL. Okay, so then you will get, after simplification, E square divided by 4RL. Okay, the maximum power is E square divided by 4RL. So the voltage across the load is, so what will be the voltage across the load? Voltage across the load is half the open circuit voltage at the terminals A and B. Okay. So overall efficiency of the network supplying maximum power to load terminals is 50 percentage only. So efficiency will be 50 percentage. At the time the load will be maximum, and the maximum power formula also we have seen, that is E square by 4 RL, and the voltage across the load will be half of the open circuit voltage. Okay, that is P by 2. So half of the power is wasted in the network. Okay, so only half of the power only consumed by the load. So the application of this theorem to power transmission and distribution networks is limited, because in their cases the goal is high efficiency. Okay, so this theorem is applicable and widely used in communication networks, because in their case the goal is either to receive or transfer maximum power. So that is why this logic is used only at the communication networks, not in the distribution and transmission. Okay. So okay, fine. We will solve one problem so that you will get a much more idea on this theorem. Okay. So calculate the value of load. So this is a circuit given. Calculate the value of the load resistance for which maximum power will be transferred to load, and also calculate the value of the maximum power. Okay, so this is a given load. So here 100, given circuit, this is 100 volts, 10 ohms, 15 ohms, 10 ohms, and RL. The solution. The maximum power is transferred to load when the resistance of the network is equal to the load resistance. We know that, okay, as viewed from the load terminals. Hence, remove the battery and put it with the internal resistance. Here, internal resistance is not there, so we have closed it, okay. Hence, remove the battery and calculate the resistance as seen from the load terminals, okay. So, here, remove the battery and short it. Now, you can see here, if you observe from uh, AB terminal side, then 10 and 10 ohms are in parallel, and this combination will be in series with 15 ohms. Okay. So here 10 and 10 are in parallel as shown in figure, and this combination in series with 15 ohms. So the total resistance is, so 10 and 10 ohms are in parallel. That result will be 5 ohms plus 15 ohms. So the total resistance is 20 ohms. Okay. So the load resistance is 20 ohms. Okay. So we have found the RL value, that is 20 ohms. So the circuit is shown in figure. Now the total resistance as seen by the battery. So from the battery, if we see what happens, these two are in series. Now you can find out the total resistance, actual resistance. Okay. So wait, we will solve it better. Okay. So now here 15 plus 20, 20, 35. Okay. So 35 is in parallel with 10. So 35 into 10 divided by 10 plus 35. Okay, you will get, and the value which you got will be in series with the 10 ohms. Okay, so here 10 plus 35 is 45. So 35 into 10, 350 divided by 45. You will get 7.778. Okay, so which is equals to 7.778. Okay, so now this will be in series with 10 ohms. So the total resistance will be 17.778. Okay, which is equal to when you viewed from a battery side. Okay, so we found RL and also we found the total resistance. Now we have to find the current. Okay, so the current is supplied by the battery. So what is the current supplied from the battery? I is equals to voltage divided by the total resistance. So this is a battery which is equals to, we got, that is 5.62 amps. So this is a the current. But what we need that IL current, not the total current. Okay, so the current which is supplied by battery, but we need the current which is flowing through the load. So we have to apply here a current division method. Okay, from by the current division method we can get IL. So IL is equals to the total current into, so you want across, so you want across, so this, right, So the current which is, so from here you will get 5 points, and so the current you want on this, so 10 in 10 divided by 35 plus 40, 35 plus 10, okay. So 35 plus 10, that is 45. So 10 divided by 35 plus 10, 45. So you will get 1.25 amps. So this is the current which is flowing through 20 ohms resistance, okay. So now we have to even find out the power. So power is equals to when what is power actually transferred when maximum power transfer. So at that time, that is E square by 4RL, okay. So this is sorry, you can calculate like this also, I square into R, okay. So I square is 1.25 whole square into RL is 20, so which is equals to 31.20 watts. So this is the power transfer. You can even calculate by that law also, okay. Hmm. So we have solved one problem on the uh, maximum power transfer theorem, okay. And we have discussed about the expression how we have got the maximum power transfer theorem to the loads, and what is the current, and what is the power uh, when it is when the power is transferring maximum, and what is the efficiency also, and the application also. It is not suitable for the transmission distribution, and rather it is suitable for the communication networks, okay. So we will see some quiz points that maximum power transfer theorem is used for communication networks. Just now we discussed. Okay. And the maximum power is delivered to load. What is the efficiency? Efficiency is 50%. So hope today's theorem, I mean in this session, the theorem, that is maximum power transfer theorem, is understood to you all. So till now we have discussed almost all of the theorems, that is from the Ohm's law, Kirchhoff laws, current law, voltage law, Thevenin's, Norton's, and now maximum power transfer theorem. So these are all theorems and laws. If you remember, that is more than enough to solve the networks. Okay, so you have to remember all the laws and the statements, and you have to apply it. See, you can solve any network with by knowing even one of the theorem, but if you know all the theorems, you can solve any complicated network also, okay. So hope today's session is understood to you all. Thank you for today's session. We will meet in the next session. Thank you so much.